A random variable is a numerical outcome of a probability experiment. Random variables are usually denoted by uppercase letters. A discrete random variable is a random variable whose possible values can be listed. The list may be infinite, for example, the list of all whole numbers, okay? We did have a little issue with that on the last test, I think, that some of us weren't quite sure about discrete versus continuous. And discrete's individual things that we can list, okay? A continuous random variable are random variables, and I apologize for that main content that's right there. When I went to do the screen snip, it threw, and I hovered over the textbook part, it popped up main content. That's not supposed to be there. This should say continuous random variables are random variables that can take on any value in an interval. The possible values of a continuous variable are not restricted to any list, okay? So 6.1, it's pretty easy, it's pretty nice. I'm sure there will be homework questions like it. Which of the following random variables are discrete and which are continuous? So A says the number that comes up on the roll of a die. Is it discrete or is it continuous? It's discrete because we can list what could come up, right? It's going to be 1, 2, 3, 4, 5, or 6. So it is discrete. Okay? The height of a randomly chosen college student. That one's continuous. Okay, because we're not going to get, let's say, just a 6 foot tall or just a 5 foot tall person, right? You're going to get anything in between, probably from 4.5 to 6.5, 7 feet tall, right? The number of siblings a randomly chosen person has. That is discrete. Because here's the deal, guys. We can't get 2.5 siblings, right? That's why that one's discrete. We either get 1 sibling, 2 siblings, 3, 4, 5. You're getting whole numbers there, okay? Amount of electricity used to light a randomly chosen room. That is continuous. Okay, good. A probability distribution for discrete random variable specifies the probability for each possible value of the random variables. That doesn't make a lot of sense. Let's look at what's going on. Example 2 says a fair coin is tossed twice. Let X be the number of heads that come up. Find the probability distribution of X. Okay. So, the first thing we're going to do is we're going to make a table, okay? So, we've got first toss, and we've got second toss. And we're going to list all the possibilities that we could get. So, we could toss the first time and we could get a head, right? And we could toss again for the second time and get another head, right? We could toss the first time and get a head. We could toss the second time and get a tail. Or we could toss the first time and get a tail, and the second time get a head. Or we could get a tail and a tail, right? So, X is the number of heads that come up, okay? So, what is the probability that we get 0 heads? How many of those choices, how many total combinations are there right there? There are 4, right? So you do a toss and a toss, that's 1. A toss and a toss, that's 2. A toss and a toss, that's 3. A toss and a toss, that's 4. So there's 4 possible outcomes right there. Right? Out of those 4, how many have no heads? We don't get a head. 1. So the probability of 0 heads is 1 out of 4. Okay? So we would say P of 0 equals 1/4. Because X is the number of heads that come up. Okay, that's where I'm getting that from. It told me that in the problem. All right, so let's think about what is the probability of getting 1 head. We just get 1 head. 2. 2 out of 4, right? There are 2 outcomes where I have just 1 head, and the other flip is a tail. Okay, so I say the probability of 1 equals 1/2, right? With 2 out of 4 is 1/2. You agree? I'm just rewriting, instead of leaving head on there, I just make it P1. Because you'll see it on your homework, you won't see P1 head. You'll just see P1 or P0, okay? So let's talk about the probability of 2 heads. Okay, what's the probability that I get 2 heads? 1/4, okay? So the probability of 2 is 1/4. What do you notice if we add all those up? If I add up the probability of 0 heads, 1 head, or 2 heads, what's 1/4 plus 2/4 plus 1/4? 1. And that's really important. We're going to say notice all probabilities are between, there's actually 2 things to notice here, between 0 and 1, and they total 1. Now, they do ask you to find the probability distribution of X, and they set this up in a table. They generally don't just list it, P of 0 is 1/4, P of 1 is 1/2, P of 2 equals 1/4. They don't list it like that. They'll use a table that's kind of sideways, and they'll give you X, they'll say X, and they'll say P of X, the probability of X. So when X is 0, what did we find that probability was? 1/4. Okay? And that's a little 1/4. When X is 1, what is the probability of 1? 1/2. So they list on half. And then 2, they're going to tell me 1/4 again. Okay? You will also possibly see it written in their decimal form, 0.25, 0.5, and 0.25. Okay? We really get to talking about probabilities now as far as decimals and being in percentages. So you have a 25% chance of getting what? No heads at all. You have a 25% chance of getting 2 heads. But you have a 50% chance of getting head-tail because you have head-tail or tail-head.
So it says let X be the number of heads that come up.
Mm-hmm.
Why did we find the probability of 0 heads then?
Because that is the probability of no heads. That is still a number of heads. 0 heads is no heads. I know it seems silly, but
So all of those are the answers to example 2?
yes. This table right here, pretty much, not necessarily written in double form. This table is the answer to number 2.
Okay.
They'll generally ask you to fill out a table like that. And that's why I went ahead and listed it in table form. I knew you guys understood this P of 0, P of 1, P of 2. But when you get to your homework, it'll be a table like that. And you're going to be looking at me going, oh, she didn't know table. And which, if I didn't write it, we didn't. But you have to put the probability of no heads. because we have problems later on where it goes at least one head. And when we do the at least problems, you say 1 minus the probability of none. And so you have to be able to find the probability of no heads. Okay? So the probability of at least 1 head would be 75%. But, okay, properties of discrete probability distributions. And you proved these right here. Number 1, the probability of X is always between 0 and 1. If you get a negative, guys, it's wrong. Okay? It's between 0 and 1. And then you also proved that the sum, remember that little sigma means sum, if I can draw it correctly. The sum of all the probabilities together will equal 1. Okay, let's look at example 3. All right, it says, which of the following tables represent probability distributions? Well, guys, these are going off those 2 properties that you wrote. First one that I would check is you need to make sure all the probabilities are between 0 and 1. That means they have to be positive and they can't be a decimal greater than 1. And that's real easy to tell. That's the first thing you look for. So in A, is A a probability distribution? No, because we find P of 3 equals negative 0.30. And we can't have a negative. Everybody's got it between 0 and 1. Okay, and that's all you got to say is no, actually. B. Okay, well, we see that everybody's between 0 and 1, right? So the next thing we have to check is, do all of those add up to be 1? Okay, so the first thing we checked was for all X, are they between 0 and 1? And that was yes. So now let's add up the sum of those probabilities, and we're checking to see if they equal 1. So I've got 0.17 plus 0.25 plus 0.31 plus 0.22 plus 0.05. And somebody tell me what they get. Did you get 1, Raina? Oh, I'm sorry. I thought you held up your hand like this. Like, yeah, it's 1. Megan, did you put them in there? You're working on it. Robert, you're my king of the calculators. Look at it. It is 1. Good. Robert, is this the first time you've taken this class? Yeah, okay. You just like using your calculator that much.
If I can find a way to do it easier, I will.
Yes, and it actually does help you in this class to, and you're really going to find that out today when we do 6-2, because you can do that binomial PDF and binomial CDF, and all you got to do is put in 3 numbers versus trying to calculate a whole big thing. It's much nicer. You just got to know when to use it and how to use it. Okay, so this is a yes. All right, C. Okay, is C going to be a probability distribution? Nope. That's a no, because P of 1 equals 1.02. And that's a nah. That one's out. D. Everybody's between 0 and 1. So that check gets done. But so now we need to check if they add up to 1. It adds up more than 1? Okay. We're just going to say, I don't even need to know. We're going to say that it is greater than 1, so it's a no. Okay? All right, not too bad, right? That's pretty simple. First, we picked out if it's discrete or continuous. Then, now here we picked out this probability distribution. We did do a little probability table, okay? Example 6.4. 4 patients have made appointments to have their blood pressure checked at a clinic. Let X be the number of them who have high blood pressure. Based on data from the National Health and Examination Survey, the probability distribution of X is the following. Okay, so guys, it's pretty simple, but you gotta know how to read the table. Okay, so the probability that none of them have high blood pressure, that's the 0, is 0.23. Okay? Because we have 4 patients. The probability that one of them does is 0.41, 2 of them 0.27, 3 0.08, and all 4 having high blood pressure are 0.01. I'm going to tell you right now, I could take a room of people, and if I picked the right profession, everybody in there would have high blood pressure or be on high blood pressure medicine. And you guys that are in healthcare know that right now about who you see coming to the clinic. I mean, you just do. Unfortunately, that's just the way it is. Okay, so it says find the probability of one patient having high blood pressure. So what's that going to be? You just read the chart. 0.41. Okay. Now I want the probability of 2 or 3. Now these are they're mutually exclusive, right? One doesn't have anything to do with the other. So I can just literally find the probability of 2 plus the probability of 3. Okay, so that's going to give me 0.27 plus 0.08, which is actually, 0.35. Okay. C asks me the probability of more than 1, so we're not going to include 1 there. So that's the probability of 2 plus the probability of 3 plus the probability of 4. So that gives me 0.27 plus 0.08 plus the 0.01, which just gives me 0.36 because all I did was add 0.01 to the previous one, correct? Because I already had 2 and 3. I knew they were 0.35. And then at least 1. Now, this is where, and Raina, this is where you're part of and Jorge scratching off his lottery tickets, because that was the problem that you had. When we say at least 1, guys, you could add up the probability of 1, 2, 3, and 4, but that's a lot, right? Especially, it's not a lot here, but let's say we had 10 people, okay? Or we had 100 people. You wouldn't want to add all those up. So it's easier to say, well, that's really 1 minus the probability of 0. Because all of them added together have to equal 1. And if you want at least 1, that means you want the probability of getting 1 person, 2 people, 3 people, and 4 people. And all that is 1 minus no people having high blood pressure is what that is, okay? Because that's the only one you're leaving out. That's why we find the probability of no heads, okay? So that's going to give me 1 minus 0.23, which does give me 0.77. And guys, I'm telling you, if we go over here and we found it the other way of at least 1, that would have been the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4. Well, the probability of 1 is 0.41, and then you found 2, 3, 4 above, right? That's 0.36, and sure enough, that's 0.77. You get the same thing. It's just less work and less button pushing in that calculator to just go 1 minus 0.23. Okay? The next part, we list a few rules that you already knew. The mutually exclusive, you knew this. We talked about this already. I don't remember which section. I do remember it's in this unit. You You guys do so much work in one sitting, it's hard for me to remember which particular section it comes from. So the probability of A or B is going to equal the probability of A plus the probability of B, as long as they're mutually exclusive. Do you remember when we have to, what do we do if they're not mutually exclusive? We have to subtract, yeah, A and B. Good. The rule of complements, this is the one where I'm talking about. That little C at the top means the complement of A. That's everything other than A, is what that stands for. This is the rule that we used on D. You can make yourself a little note there if you want to. Used on D. We use this one a lot on the at least, because you're talking about everybody but one thing, okay? And then we have the probability of at least one. This was your 1 minus P0. That is what we did on D. Those are kind of combined together. Okay. Of at least one, that's everybody but the 0 of it not happening. Usually those numbers are fairly high. Those probabilities are fairly high. They're usually in the 90-somethings. But a school teacher flips a coin and uses the results to determine whether to start the school day with a math lesson or a history lesson. If the first lesson is recorded for 3 consecutive days, there are 8 possible outcomes. Math, 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 history, math, history, math, math, history, 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 math, math, history, math, history, 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 math, history, 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 for all 3 days. Assume these outcomes are equally likely. Let X represent the number of days that start with a math lesson. Okay. So there's 3 days. She flips a coin, and half the problem is understanding what the problem is talking about. And this one was a little, I was like, what are we talking about? For 3 days, she was going to start the lesson based on the flip of a coin. Okay? One side was math, one side's history on the coin. So she flips the coin. And then the outcomes that you see here are what could have happened. Now, she's still teaching both math and history in the day. It's just how she's going to start that day. Okay? So, on the first day, she could flip and she could get a math. On the second day, she could flip, she could get a math. On the third day, she could flip and she could get a math. Okay? That's where that's coming from. Then we could do a math, and then that third day, you start with history. Or we could do a math, history, right? Or we could do a history, math. Or history, math, history, math, history. Y'all see where I'm going with that? Okay. All right. So, we need to find the probability distribution of X. That means we need to make the table, okay? So we've got my X, we've got my P of X, and we need to talk about what X represents. What does X represent there? The number of days that start with a math lesson. Okay, so there could be 0 days. Out of the 3 days, you could have none of the days. You could not flip heads or flip math any of the time on all 3 days, right? And you would start with history. Okay, or there might be 1 day that has math, that you start with math. Or there could be 2 days, right, that start with math. Or all 3 days could start with math. Okay, that's it. There's only 3 days, guys. So either all 3 days start with math, 1 of the days starts with math, 2 of the days starts with math, or 3 of the days starts with math, right? Okay, so how many total? So let's find a P of 0. And we're going to write these in our chart in decimal form, okay? How many total outcomes are there first? 8. And they even tell you that because I think they realized when they were writing the problem, it was a little confusing. Okay, so out of those 8 outcomes, how many don't ever start with math? None of the 3 days start with math. Well, I don't mean start, but don't have math at the, I don't mean day 1 is not math. I mean, you don't see math in the outcome at all. 1, right? 1 of the days. Well, there we go. Let me see where it's at. The history. That means the history means that on the 3 days, we never started with math. Day 1, we started with history. Day 2, we started with history. Day 3, we started with history. So that's the probability of never flipping math. Okay? What is 1 over 8 as a decimal? Good. 0.125. Good. Okay? All right. Now, let's do P of 1. Okay? 8 total days again. Out of those 8 total days, or 8 total flips, right there, how many outcomes have just math once? 3 days. 7? No, just math one time. Just one time. 1 math. 1, 2, 3. You only see 1 math in the set of 3. Okay. Yeah, I'm going to tell you, I had issues when I first worked it because I was like, I'm getting 24 days here. I'm like, there's 8 and then we got 3. But that's not, 8 are the possible outcomes that you could get from the 3 days of flipping. What is 3 over 8 as a decimal? Good, 0.375. I should have made my chart bigger. Okay? All right, what's the probability that 2 of the days are math? How many? 1, 2, 3. Good. 3 out of 8. Okay, what's 3 out of 8? Oh, same thing as the other one, right? 1.375. And then all 3 days are math. We're back to 1 out of 8. Which is 0.125. If you add all 4 of those up, do you get 1? Yes, that means you did it right. This is your answer. You will fill in a table like that in 6-1. Okay? Let's look at 2. 2 says, someone says that the following table shows the probability distribution for the number of boys in a family of 4 children. Is this possible? Well, okay, I'm not worried about the scenario of the problem. I'm looking at this table. I'm going, okay, well, it is, everybody's between 0 and 1, so that box is checked. Now, the next one I got to ask myself, do they all add up to 1? No, what do they add up to? 1.37? Okay, so the summation of P of X equals 1.37, so this is no. Because that is greater than 1. Good job. At least this section has lots of examples on it, so we're practicing. It's not just a whole bunch of vocabulary. All right. Why are we doing this again? Is this the same one? Oh, no, it's not. Okay, so 3 says, which of the following tables represent probability distributions? Okay, they've given you a choice, which one's probability distribution, which one's not. They make these a little more difficult because everybody is between 0 and 1. So we need to add them up. So tell me what you get. Y'all tell me how many are yes and how many is no. Y'all usually work all three. What'd you do? 2 of them are good. Which ones? A and C. Good. A and C are your yeses. B is a no. I got 0.87 plus 0.25, so like 1.13 or something. 1.12. Okay. So we have the probability of P of X equals, 1.12. So that one's a no. That one's pretty nice, right? Let's look at 4. Following is the probability distribution of a random variable that represents the number of extracurricular activities the college freshman participates in. So the probability, so let's read the table. So the probability that the college freshman participates in 0 extracurricular activities is 0.06. So it's about 6% chance. The probability that they participate in 1 extracurricular is 0.14. 2 extracurriculars is 0.45. 3 extracurriculars are 0.21. And 4 extracurriculars are 0.14. Guys, if you need to write on there what that is, write what it is. Those X represents the number of extracurriculars, okay? Find the probability that a student participates in exactly 2 activities. So I want the probability of 2, which is going to be what? 0.45. Okay? Find the probability that a student participates in more than 2 activities. So if it's more than 2, that means it's the probability of 3 activities plus the probability of 4 activities, correct? So I've got 0.21 plus 0.14, which is going to give me 0.35. You agree? Okay. Last one, find the probability that a student participates in at least 1 activity. So that means 1, 2, 3, 4. I'm going to do my 1 minus P of 0. Okay. So I've got 1 minus P of 0 is going to equal 1 minus 0.06, which should give me 0.94. There's a 94% chance that the student is going to participate in at least 1 or more extracurricular activities. Okay? All right. Constructing a probability distribution that describes a population. An airport parking facility contains 1,000 parking spaces. Of these, 142 are covered long-term spaces that cost $2 per hour. 378 are covered short-term spaces that cost $4.50 per hour. 423 are uncovered long-term spaces that cost $1.50 per hour. And 57 are uncovered short-term spaces that cost $4 per hour. A parking space is selected at random. Let X represent the hourly parking fee for the randomly sampled space. Find the probability distribution of X. So we set up our table. We've got X. We've got P of X. Okay. It says let X represent the hourly parking fee. So I know it's the hourly parking fee. Okay. Guys, what I did, now be careful when you do your homework because they're probably going to, if there's a problem like this, they'll list those values from least to greatest. I literally listed them from the way they were listed in the problem because it doesn't really matter. Just be careful when you are filling them in on the homework that you notice if they are least to greatest and not just in the order that they're listed in the problem. So I know that there's some that are $2 per hour, right? Then I know I've got some that are $4.50 an hour. That seems like a lot, guys. There's $1.50 an hour. And then $4 an hour. Okay? Now, we're going to list P of X in terms of a decimal. So below this, I'm going to find the fraction, and then you guys can find the decimal. We'll find the decimal. So let's say the probability of it being a $2 an hour slot. Okay. Well, how many of those are there? 142 out of how many total? 1,000, right? Which as a decimal, that should just be 0.142. Correct? I just moved that decimal place 3 places to the left because I was dividing by 1,000. Okay, so let's do probability of $4.50. How many of those are there? 378. 378 out of 1,000. And that should give me 0.378. Okay, the probability of $1.50 slot, there's 423 of those out of 1,000. So I've got 0.423. And then the probability of a $4 slot, or what, 57 out of 1,000, which is 0.057. So about 6% right there. Okay, this is what we're looking for. What your homework will ask you for is this table right here. Okay. Number 5 says there are 5,000 undergraduates registered at a certain college. Of them, 478 are taking one course, 645 are taking 2 courses, 568 are taking 3 courses, and 1,864 are taking 4 courses. 1,357 are taking 5 courses, and 88 are taking 6 courses. Let X be the number of courses taken by a student randomly sampled from this population. Find the probability distribution of X. Okay, so we're making our table. I've got X, I got P of X, and this time it says let X be the number of courses taken by a student. So this is number of courses. Guys, if you'll just make that little side note yourself on there, that does help you make the table make more sense because you can kind of talk it back to yourself on that one. So we've got 1 course, I need to give a little more room there. We've got 2 courses, 3 courses, whoo, that line's bad, 4 courses, 5 courses, and 6 courses, right? 6 courses should be around 18 hours, okay? Okay, so how many total students were there? 5,000, good. So the probability of getting a student that's taking 1 course is how many out of 5,000? 478. You will need a calculator for that one. 478 out of 5,000 gives me what as a decimal? Good. 0.0956. Okay, probability of 2. We've got 645 students taking 5,000. 645 students out of 5,000 taking 2 courses. Decimal on that one.
0.129.
Good. 0.129. Okay. Probability of the student taking 3 courses. I have 568, I think, out of 5,000.
0.1136.
Good. 0.1136, about 11%. The probability of 4, 1864 over 5,000.
0.3728.
Good. Can anybody tell me why that is the highest one? That's full time. And in order to usually get your financial aid or scholarships, you got to be a full-time student. Okay. Probability of 5 courses is 1357 over 5,000, which gives me 0.2714. People will often take 5. That way, if something happens and they need to drop down, they don't fall below their required hours as a full-time student. You can drop a class and you're down to 12. That is, yeah, y'all told me 2714. And then the probability of 6 are 88 out of 5,000, which gives me
0.0176.
good. That's only about 2% of the population that will take up to 18 hours. And if you take over 18, such as 21 or 24, that used to have a dean's approval to do that, because it's not likely that you're going to be that successful. I have taken 21 in a semester before, but that was back when I was a music major. And you had so many ensemble hours that you had to do that they added up on top of your normal classes, and they would easily sign for us to have 21 hours. But that's been a long time ago. Number 6, good job. That table is your answer, minus the number of courses. Oh my goodness. Okay, number 6 says, following is a probability histogram for the number of children a woman has. The numbers on the tops of the rectangles are the heights. Okay, so guys, and I only stress this because we had a little trouble reading those graphs on Unit 1 test. We had a little, it was about the movies, the frequency of the people, and like 0 movies was down here, and the frequency number of people, it would have been, you guys would have been okay if instead of frequency it said number of people. And then you go, oh, okay, there's 10 people that saw no movies this month. Or there's, so let's just make sure we can see what's going on. So these are the x-axis, the horizontal axis is the number of children, okay? You'll note that. So the probability of 0 children is actually 0.273, okay? That the woman has no children, there's about a 27% chance that you're going to get a woman that has no children. This does not tell me the age of the females or the age range of the females. That makes a big difference. But 1 child, 0.16. 2 children, 0.24. 3 children, 0.15. 4 children, 0.08. 5 is 0.039. 6 is 0.02. 7 is 0.01. You only got about 1% chance that they have 7 children, and about, actually, the percentage of the probability of having 8 children is higher than the probability of 7 children. That's interesting. Okay, what is the probability that a randomly chosen woman has exactly 2 children? What is it, guys? Yeah, you are literally just reading that graph. What is the probability that a randomly chosen woman has fewer than 2 children? So you don't include the 2. You're doing probability of 0 plus probability of 1, which is 0.273 plus 0.160, right? What'd you get?
0.433.
Good. Okay. And what is the probability that a randomly chosen woman has either 4 or 5 children? So the probability of 4 plus the probability of 5 should be 0.082 plus 0.039, which is
0.129.
good. Only about 12%. Okay, that's all that. All right, we need to talk about how to find the mean. Did I actually write that there? Yes, and then I need to add a little stuff there for you. To find the mean of a discrete random variable. I did not type that well. Multiply each possible value by its probability, then add the products. Okay, so that's a little different than what we've done when we found the mean. Usually to find the mean, we add up all the values, divide by the total, and we're good to go, right? Because you're finding the average. This one's a little different, okay? So that is going to be the summation of x times the probability of x, okay? So what you do, like on that last one that we did, you would go, okay, 2, when x is 2, having 2 kids, you multiply that times the probability of having 2 kids. But then you do all your values like that, okay? So over here, we would have said to find this, to find the mean of the discrete random variable, we would have gone 0 times 0.273 plus 1 times 0.160 plus 2 times 0.244 plus 3 times 0.154 plus 4 times 0.082 plus 5 times 0.039 plus 6 times 0.020 plus 7 times 0.011 plus 8 times 0.017. Okay, and that is using that formula the summation of x times p of x. Okay? If we add all that up, if we put that in the calculator, plus 2 times 0.244, plus 3 times 0.154, plus 4 times 0.082, plus 5 times 0.039, plus 6 times 0.020. And I didn't pre-work this, just threw this one in there for the fun of it. Okay? What is the mean average used to, and here's how it goes. What do they used to say? The average number of children per family was what? 2.5 children per family. What did we get on this set of data? Nobody else put it in there? Megan's going. Keep going, Megan. Oh.
Yeah.
Okay. Here's what I'm getting. 1.966 children. Okay? That is the mean of that discrete random variable. Another name for that is called the expected value. And this is where we get into if we're gambling, if we're betting on horses or dogs or something of that nature, and you're looking at the expected value that your payout's going to be. Okay? So over here, another name for the mean of a random variable specifies, this doesn't make, I'm telling you, when I typed this up, this did not go well. Like, I originally had this written out and I went back and erased and typed for you. I should have just left it written. Another name for the mean of a random variable is the expected value, or E of x, okay? All right, let's look at example 6. It says, a computer monitor is composed of a very large number of points of light called pixels. It is not uncommon for a few of these pixels to be defective. Let X represent the number of defective pixels on a randomly chosen monitor. The probability distribution of X is as follows. So they gave you the table. It says find the mean number of defective pixels. Okay, so we're looking on average how many defective pixels are we going to have. So we know that we are going to multiply X times its probability, add all that up, and that will tell us the expected number of defective pixels, okay, per computer screen. So I've got, of course, 0 times 0.2 plus 1 times 0.5 plus 2 times 0.2 plus 3 times 0.1. Okay, when I add all that up, what do I get? Good, 1.2. What that means is that we can expect 1.2 defective pixels per computer monitor. Okay, that's what that means. Let's see if we sample items from a population and as the sample size grows larger, the sample mean will approach the, okay, that one wrote correctly. Law of large numbers for means. If we sample items from a population, then as the sample size grows larger, the sample mean will approach the population mean. We've talked about that before, about having a large enough sample size, and as the sample size gets bigger and bigger, then it approaches the population, okay? A true-false quiz with 10 questions was given to a statistics class. The following is the probability distribution for the score of a randomly chosen student. Find the mean score and interpret the result. Okay, so let's think about what this table is showing us. What is it really telling me? What does X represent? I just didn't hear you, Raina. I'm sorry. Oh no, we're on 7. It's okay. And number 7. So what this shows me is we've got, what it's representing is there's 10 questions on the test. Okay? And those are actually scores out of 10. So the student scores anywhere from 0 to 10. Like each question is worth 1 point. Like sometimes your homework questions will be out of 10. Or they might be out of 20. That kind of thing. It won't be out of 100. So the probability that the student scores a 5 out of 10 is 4%. The probability that they score a 6 out of 10 is 16. 7, 36, 8, 24%, 9, 12%, and getting all 10 correct, making that 100, 10 out of 10 is about an 8% chance. Okay? Is what that's saying. So, they're saying from this, now let's find the mean score. Okay? So, since it tells me to find the mean score, I'm going to say 5 times the 0.04 plus 6 times the 0.16 plus 7 times the 0.36 plus 8 times the 0.24 plus 9 times the 0.12 plus 10 times the 0.08. Okay, so you're finding the average score on this test for a typical statistics student that takes it, is what you're doing. Okay. When we multiply all those and add those up, is somebody going to beat me? Huh? Yeah. The average score is 7.48. We expect the student to make somewhere around a 7.5. 7. So we would say probably 7 to 8. Okay? And when it says it's just the average score is 7.48, we don't have to tell why. All right, what's next? Are we still going on 6.1? 6.2 is not long at all. Variance of a discrete random variable. Woo! Huh? 7.48. Okay, the variance of a discrete random variable x is, and they give you a big long formula, right? And then they do the standard deviation, okay? And of course the standard deviation is just the square root of the variance, just like it always has been. Remember when we started out talking about variance and standard deviation, we always take the square root of the variance. Do we need to take a break? Y'all need a break? Y'all okay? I was going to keep going until we finish 6.1 and then you could take a break. Raina's like, just get it over with. Okay, so the way we're going to find that, we still have a square going on here. We do have, okay, we're saying x minus sigma x, which that's the mean. Remember, we did that before when we found the variance. We'd say x minus the mean squared, but this time we say times p of x. Okay, in the old one, we had x minus the mean squared, and then we added all those up. Remember when we made the big table, the big long table, and then we would say, what is x minus the mean? And then we would square that, and then we would add all those up, and then we divided by n. unless it was a sample and we divided by n minus 1. Okay, so this one is much the same. There's no divide by n, but you subtract it, you square it, and then you multiply it times p of x. Then, when we want to find the standard deviation, we just take the square root of that variance. Okay? That's all it is. And of course, when you take your test, you're going to have access to your formulas. It's fine. Y'all like, yep, we sure are. 6.6, we presented the following probability distribution for the number of defective pixels. We're back to our pixels here in a computer monitor. Compute the variance and standard deviation of the number of defective pixels. Well, is this the same chart that we had in the previous example? Because if it is, I'm going to use that mean. Yep, it sure is. So what did we get for the mean on the pixels before? Oh, thank you. 1.2. Robert knows I love these cookies. And I hunt them down. And I'm feeding my type 2 diabetes. Technically, Robert's feeding my type 2 diabetes, but he only gets them every now and then. So I personally am feeding my type 2 diabetes. I do not have type 2 diabetes, by the way, but I'm on the right path, aren't I? Okay, so my mean was 1.2, right? I'm going to use that. I've already found it. I'm not making you recalculate that. So now we just need to we're going to find the variance first. So the variance is going to equal, all right, so we've got the summation of x minus, I'm just going to write the whole, I don't want to write the whole thing. So I need to find x minus each one of those squared, right? Do we want to make a table? Y'all liked making the table last time. Okay, so we had, this is going to be x minus the mean of x. So I've got 0 minus 1.2. I need to make that bigger. I don't remember how we made our table. Evidently larger than that, though. Okay, and then I've got 1 minus 1.2. Then I have 2 minus 0.2. And then I have 3 minus 0.1. Right? Oh, I did make a table on here. Okay? And I'm going to run out of room. Okay. All right? So that's going to give me negative 1.2, right, in that first one. And then I'm going to get what? Negative 0.2. Everybody agree? Then I'm going to get a positive. Uh-oh, I messed up. Why did I switch, guys? We're subtracting the mean. It's because those cookies came around. I got a little excited. 2 minus 1.2 is 0.8. And then 3 minus 1.2 is 1.8. Okay? All right. Now, you're ready to square that. So we're going to say x minus mu squared. So that means you're going to square the negative 1.2, the negative 0.2, the 0.8, and the 1.8, right? Okay, so if I square the negative 1.2, if I can type it in correctly, I get 1.44. You agree? 0.2 squared is going to give me 0.04. 0.8 squared should give me 0.64. And 1.8 squared is going to give me 3.24. Okay, now I also have to do that. What do I have to do now before I can? I've got to multiply them all times their p of x, right? Okay, well, for 0, p of 0 was 0.2. P of 1 was 0.5. P of 2 was 0.2. And then P of 3 was 0.1. So now I need to multiply those together, right? So here's what I'm doing over here. I'm doing x minus the average squared times P of x is what that's going to be. So I'm taking those two columns and I'm multiplying them together. Do y'all see what I'm doing? I'm going to multiply these two columns together. Then I got to add them up. Okay? So, when I multiply that together, 1.44 times 0.2 gives me 0.288. Okay? 0.04 times 0.5 is 0.02. 0.64 times 0.2 is 0.128. And 3.24 times 0.1 is 0.324. Now I need to add them all up. Because what does it tell me? It tells me this is the sum of x minus the average squared times p of x. Okay, this is the variance, guys. All right, so let's add them up. What'd y'all get? Right. Yeah. 0.76. Now it also tells me to find the standard deviation. So all I got to do is take the square root of that, which is going to give me 0.8718. It's a standard deviation. Let's think about what the standard deviation means, okay? We said the mean of those pixels, the average of defective pixels was 1.2, right? Then we're going, well, one standard deviation away is 0.87. So remember, that would be you add 0.87 to the 1.2 and you subtract 0.87 from the 1.2 to fall within one standard deviation of there, okay? And if this data is symmetric, we can use the empirical rule, and we know that within one standard deviation, what is that, like 68%, and then two standard deviations was 88.9 or something like that. Remember, it had that strange one, and then 3 was almost all if it was empirical. And then if it wasn't, it was Chebyshev's. Chebyshev told you he started at 2 standard deviations. He didn't start at 1. Okay, good job. This is what you were looking for, not for me to try to touch the thing. You were looking for the variance, and you were looking for the standard deviation. Okay, the following is brought to you by... The following is the probability distribution for the age of a student at a certain public high school. Okay. 3%, to be 13, there's a pretty much 8% chance that the student will be 13. There's a 24% chance that the student will be 14. a 23% chance that they're 15, 16, 28%, 17, 14, and 18 is 3%, which that's high school's a little strange. But okay, find the variance of the ages. Okay. So, what are we going to have to do? We're going to have to find the mean, right? Let's think about it. I'm thinking we should be able to put this in the calculator. And then you put that frequency in list 2, and then you give it to you. Let's try it out, because I'm not wanting to make that whole chart when we got a calculator here. Let's go do a stat edit. And in list 1, I'm going to put, y'all need me to do the camera on it so you can see? Y'all have it in there by the time I get the camera pulled up. Okay, so let's see, where am I at? Where did that go? So I've got 13, 14, 15. Well, I typed 15 2 times. 14, 15, 16, 17, and 18, correct? And pretty much we're going, well, that probability is 0.2. I don't think it'll find the right, not 0.2, 0.08. Then we've got 0.24, 0.23, 0.28, 0.14, and 0.03. Okay. So let's go to stat. I'm thinking it's probably not going to work. We're going to count. We're going to calc. We can still do
You gotta do L1 there and then
L2. Second, L2. So that is actually the number 2 button. See how it's blue? Okay. And then let's calculate it. And it's telling me that my mean is, what's it telling me my variance is there? Let's see, 1.267 for the standard deviation. Yeah, that standard deviation's right, guys. Okay, can you tell which one's the standard deviation? It's the sigma x. We're going down. It's this one right here. The sigma x is your standard deviation, okay? So it told that correctly. So all you have to do is square that number, and that'll give you your variance.
There's a way to do that too.
Yeah. Probably stat calc. Let's see. It probably isn't going to be. Let me go to. Where's my catalog? Where's VARS B? Yep. Showing me P. Okay, where's my V? Variance, looky there. Went to catalog, variance.
Where'd you go?
Second, the blue button, and 0. And then I pushed the green V, which was a 6. And variance popped up. And let's see if I do, I wonder how I'm going to have to list that. I wonder if I can list L1, comma L2. Probably not. It's not going to be that nice to me. Nope. Woo!
It worked for me.
You put in L1, L2?
I just didn't put parentheses.
What'd you do? You
I
just,
just did L1 and then L2 without the parentheses after it, and then I pressed enter. Mine works. I got 2.307.
that's probably going to be right.
Use a comma.
He didn't use a comma?
No, I didn't use a comma.
Just L1.
One L2?
Yeah, I want L2.
The book has the variance is 1.607.
Yeah, it does.
No, we're just, there you go.
Yeah. Yeah. It is, they've got the, I would go with the, until I look up what you're really supposed to do there to find that. I would go with your stat calc, your one variable stats, calculate it, produce that standard deviation, because that standard deviation is correct, the 1.267872223. Take that, square, that's your standard deviation, square that, and it will give you your variance. Don't take the square root, do the square. So you're doing 1.268, and I think that's what I did, 72233. And then guys, use the x squared button, and you get 1.6075, and that's what you're supposed to get for your variance. So put it into list 1, put the probabilities into list 2, then do a stat calc 1 var stats, produce that standard deviation, then square that, and that gives you your variance. Okay? That actually, and that's going to be exactly what I did, because that's the only reason I would have listed out that many digits so that I could produce it correctly. So we put this in, what we did over here is we put this in L1, this in L2, then we did stat, calc, and 1 var stats. Okay, then list is L1, and your frequency list is L2. Okay, hit calculate. You produce the standard deviation of x equals 1.267872233. So we went in reverse. Then we took this, then square. So we did 1.267872233 squared, and that equaled your variance of 1.6075. Okay? Because I didn't make a big chart for that. Okay, next page says applications of the mean. This is where we get to talking about gambling a little bit. There are many occasions on which people want to predict how much they are likely to gain or lose if they make a certain decision or take a certain action. Often, this is done by computing the mean of a random variable. In such situations, the mean is sometimes called the expected value. If the expected value is positive, it is an expected gain. It means you're going to make money. And if it is negative, it is an expected loss. Okay? Probability was invented by mathematicians who were hired by gamblers to help them create games of chance. For this reason, probability is an extremely useful tool to analyze gambling games. This is what it was designed to do. Okay, so a Nevada roulette wheel. Oh, I didn't delete that. I printed all that. I printed all the answers on there for you. I didn't erase it. Look, that's where I worked it out. So you don't have to write it. Okay, we'll talk through it. A Nevada roulette wheel contains 38 pockets, numbered 1 to 36 with a 0 and a double 0. 18 of the numbers are colored red, 18 are colored black, and 2, the 0 and the double 0, are colored green. Let's say you bet $1 on red. If a red number comes up, you get your dollar back along with another $1, so you win $1. If a black or green comes up, you win -$1. Winning a negative amount is a mathematician's way of saying that you lose. You lost your dollar, okay? Let X be the amount you win. Find the probability distribution of X and the expected value mean of X. Interpret the expected value. So the first thing I did is I took X. What's the probability that's going to happen? You're either going to lose $1 or you're going to win $1. There's no 0. Okay? You either lose that $1 because you made that bet and you don't win, or you make the bet, you win, and they give you your $1 and another $1 back. So there's no zeroing out. Okay? It's either you lose one or you gain one. Okay, so that's where the X's come from of -1 and 1. Now, we need to find out how I got 0.5263 for a -1. Okay, so you are betting on red, right? If a red number comes up, you get your $1 back along with another $1. Okay, so how many reds are there? 18. How many total pockets are there? 38. So you have an 18 out of 38 chance of landing on a red and gaining $1 back, right? Of getting $1, of winning $1. You get your $1 back and you win $1. Okay? Is 18 out of 38.4737? Okay? Now, let's talk about losing that $1. Where you place the bet on red, but it doesn't come up on red. It can come up on black, which there's how many of those? 18 black. And then how many green are there? 2. So there's 20 ways that you could lose, right? Out of 38. So the probability that you're going to lose $1 is way higher. Well, not way higher, but it's higher than the probability that you're going to win $1. It's 20 out of 38, which is over 50%, is 0.5263. Okay? So now we want to go, okay, well, let's say I play for a while. What's my expected value? Am I expected to lose or am I expected to win in the end? If I play multiple times, this is what this is looking like. I keep betting. Place this on red, place this on black, place this on, we didn't even talk about the green because that's way different. Well, it's not way different, but it's different. Okay, so we find the mean to find our expected value. So -1, we lose $1, times 0.5263, that's its probability. This is X times P of X plus X times P of X. Okay, that we win $1 is 0.4737. This shows me that this particular game of roulette has an expected loss value. You're expected to lose at least pretty much 5 cents. That means the house is gaining. Okay, this is per dollar, 5 cents per dollar that you play. You're gonna, in the end, you're gonna come out at a loss of 5 cents. Is what is expected to happen. Okay, the house likes that because I promise you, folks are putting more than $1 on that roulette table. So that's where that comes from. A mineral economist estimated that a particular mining venture had a probability of 0.4 of a $30 million loss, probability 0.5 of a $20 million profit, and a probability of 0.1 of a $40 million profit. Let X represent the profit in millions of dollars. Find the probability distribution of the profit and the expected value of the profit. Does this venture represent an expected gain or expected loss? Okay, so X is the amount of money that you could gain or lose. Okay, that's why the first one starts out, you could lose $30 million. You have a 40% chance of losing $30 million. Okay? Raina's going, I'm not doing this. Yeah, no, I don't have that money to, if I had $30 million, I wouldn't be, yeah, anyway. There's a 50% probability that you're going to make a $20 million profit, okay? And then there's a 10% probability that you might get a $40 million profit, okay? That's where our table comes from. And I actually listed, I just said millions on there. Okay, so now we need to find that expected value. We want to see if we actually want to go into this business adventure here. And we find the expected value with the mean. So I'm saying the negative 30 times 0.4, the 20 times 0.5, plus the 40 times 0.1. And when we add all that up, we should get pretty much a 2 million. It'll be a 2. Probably going to be 2. Because 10's 14. 2. And remember, this was in millions. That's why we're saying a $2 million. Since it was positive, that means it's a gain. So if you got that much money to throw around and possibly lose $30 million, you might as well buy into that venture, because it looks like you're going to come out, you're expected to come out with a $2 million gain in the end. Okay? Yes, there are businessmen that make decisions like this on that much money. Usually they have a financial advisor that tells them that. Financial advisors get paid a lot of money. They have master's degrees in finance, where they sit around and calculate these things all the time. Personally, I know they get paid a lot of money, but I would never want to do that. That's a lot of responsibility. It's a lot of stress. You want to talk about taking some high blood pressure pills. You could bankrupt some folks. I mean, like, yeah, no, that's not for me. No, I'll just teach you guys some math and move on with my day, and I can sleep at night. It's like I told one little nursing girl one time. She was in stats for the 3rd time, and that was the I was the gatekeeper of getting into whatever she needed to get into. And I mean, she was just bawling. She was like, she didn't want to take the test. She was crying. I said, well, you're going to sit over here and you're going to take the test. I said, because it's face-to-face and you've shown up. I said, you can cry through the whole test. I'm like, look here. I am not the gatekeeper of heaven or hell. I said, I don't keep you out of nursing school. I said, I need you to show up, and I need you to work, and I need you to try real hard, and I'm going to try to explain these things in English to you. I said, and it's going to be fine. But I was like, I'm not going to be the reason that you don't get into nursing school. Trust me. This is the 3rd time. I won't get it. I'm like, you just take the test. You take the test every time. And she showed up to class. She took her notes. She did her homework. She took her test. Didn't always do the greatest, but she passed, by God. I wasn't going to be. I said, I said, them old mean nurses over there at that nursing building, they can tell you you're not good enough to be a nurse. I'm not fixing to. I don't want to be the person that rolls in the hospital or the old folks home and you go, oh, I remember her. She flunked me in stats. That 3rd time took me 3 more years to get back. No, that's not how that's working. That is not how that's working. And I need people to take care of me when I go in there and not go, oh, you were that mean person that flunked me. Yeah, your paybacks, I'm not being that person. An insurance company sells a 1-year term life insurance policy to a 70-year-old man. The man pays a premium of $400. If he dies within 1 year, the company will pay $10,000 to his beneficiary. According to the U.S. Centers for Disease Control and Prevention, the probability that a 70-year-old man is still alive 1 year later is 0.9715. Let X be the profit made by the insurance company. Find the probability distribution and expected value of the profit. Now, this kind of math people called actuaries do, and they sit around and they find statistics and probabilities at life insurance companies, credit card companies, health insurance companies, and they figure out what's the best case scenario for the insurance company to make money and not go $9,600 in debt because the old fart kicks the bucket. So what they'll do is they'll up the rate, the life insurance rate. When this old man tries to come in, they'll go, oh no, we're probably going to have to pay out. So we need to jack that up so it doesn't cost us so much. Notice it's just a $10,000 policy. If he's getting buried, it's barely going to pay for it probably ain't going to pay for the coffin that he's going in. I'm just going to tell you, it's expensive to have a funeral. That's why I've said I'm getting cremated. Should only be around, $800 maybe, $1,000. You put me in a box. And I've already told the children where they're supposed to sprinkle my ashes so I can come back and haunt people, places we've lived before. They're over bodies of water. I'm sure that's not legal, but somebody better make it happen or I'm going to haunt them, and they know it. Okay, so the life insurance company is the X. They're either going to make $400 on this 77-year-old man or they're going to lose $9,600. Where did I get the $9,600 loss from? Minus that $400. They have to pay, if he dies, they got to pay $10,000 to help get him buried. But here's the deal. He's already paid $400. He gave them $400. So they're really only out $9,600. That negative $10,000 is $400. What he originally paid, he paid $400 that year, minus the $10,000 they're going to have to fork out if he dies within the year. Okay? So they could lose $9,600, or if he keeps living, they've gained $400. This has nothing to do with he's reading the schedule. This has nothing to do with what's best for the older gentleman. This is what's best for the insurance company and how much money they want to make is what this problem's about. Okay? So there is some actuaries sat around and they said, well, look, there's a 97% chance that this old man will be alive within a year. Evidently, he doesn't smoke. He doesn't already have congestive heart failure. He probably doesn't have high blood pressure. They take all that into account when they charge you a rate. And they send somebody out to your house to take your blood, to take your blood pressure. They measure your cholesterol count, all that stuff. Okay? And they send it all off and they go, oh, we're going to charge you this much versus this much. Okay? So there's a 97% chance this old man's going to be alive within a year. So the insurance company has a 97% chance of making $400. And how did I get the 0.0285 for losing $9,600? Subtracted it from 1. Good. This is 1 minus the 0.9715. Okay? Because it's all got to add up to 1. The probability's got to add up to 1. We've been adding up the distribution tables this whole time. Okay, so we need to find the mean now. Now we know where all the numbers came from. So I've got losing $9,600 at about a 3% chance that's going to happen, plus the $400 at a 97% chance gain. We get a mean of 115. So what that says is our expected payback rate, if we insure him, is going to be about $115. So it is a gain if they want to take that risk on X number of 70-year-olds, okay? Is what that is telling me. And that is the end of 6-1, my friends.